Hey guys, hope you're doing great. Maxim here, and today I want to present you my new work. It is a benchmarking environment with custom scoring system for Langchain semantic chunking methods. So, what are the Langchain semantic chunking methods? Yeah, chunking is an important process in NLP, natural language processing, and we normally use it when we want to input some data in a vector database to use it for retrieval augmented generation (RAG). So we cannot input the whole text. I mean, we can, but it's the best practices to first chunk it up into smaller pieces and then only turn it to vectors and put in the database. So Langchain offers a lot of different chunking methods, semantic chunking methods, from percentile to standard deviation to interquartile to gradient. Yeah, but if we go through the documentation, it's not really explicit what does even mean, how does it work, and how they're different and for which use cases they are better. Yeah, it's very limited in the description. The only thing that we can see here is that a gradient should be better for legal or medical domains. Yeah, so for this method useful when chunks are highly correlated with each other or specific to a domain. Yeah, but still we don't have any clear tests, we don't have any comparisons, so it was always kind of a question for me, what should I choose for my specific projects, right? So I came up with this idea of this semantic chunking arena of benchmarking environment, and I would like to go through the paper first and then show you some code and how it works. Yeah, so basically what I do is I conduct experiments on 100 introductions from PubMed articles on COVID-19, as well as also 100 abstracts from machine learning papers from arXiv. Yeah, and I'm using a lot of different statistic methods like cosine similarity, precision, recall, F1 score, average precision, and normalized discounted cumulative gain to evaluate the performance. Yeah, here I will be evaluating both the chunk sizes, right, as well as retrieval quality compared to ground truth that is predefined. And then at the end there is a custom scoring system that will kind of summarize it all because it has both weights distributed to chunk sizing as well as to the retrieval quality, and then combined we have a custom score that determines how good the performance was from 0 to 100, right? So we skip the introduction, let's go into the methodology, right? We are evaluating chunk sizes, as I already said, and assessing the retrieval qualities and then ranking it all. Datasets, 100 abstracts from arXiv, 100 introductions from PubMed. Now, what about the ground truth? Yeah, what it even is. Ground truth is a set of predefined questions and answers. I would say questions and three chunks that are relevant to that I've been generating with ChatGPT and reviewing it myself. Yeah, so we have question generation, relevant chunk extraction, and also metadata association. And I will talk about why metadata was important a little bit later. Yeah. So chunking methods are exactly the ones from Langchain. What about embeddings, right? I was using all mini-LM L6v2 from Hugging Face to do all the embeddings, yeah, so they're all equal. And then similarity measure, we are using cosine similarity to calculate it all. So now, what are the evaluation metrics? For chunk size, it will be mean size, median size, standard deviation, minimum and maximum sizes, yeah, so nothing crazy. For retrieval quality, as I already mentioned, precision, recall F1, AP, and NDCG. So now let's talk about scoring system and how we are distributing weights. Yeah, size score will have 40% of the relevance to the eventual final score. Yeah, it is distributed as follows: mean score will take 35%, standard deviation score 35, minimum size score 15, and maximum size score 15. Retrieval score will take 60% of the total grading, and it will be distributed as follows: precision 20%, recall 20, so pretty much everything 20%. Now, what were the challenges and the solutions? As I said, I will mention metadata a little bit later, but the challenge was to map the exact chunks to the ground truth. Yeah, because first I was trying to do it all in order and maintain this order, but I saw that the similarity results were close to zero, right? So it was definitely something wrong because it couldn't be that bad, right? And then when I started investigating, I found out that it's actually a problem of matching the relevant chunks to the relevant ground truth. Yeah, so I assigned metadata to both chunks as well as to the ground truth objects, which is a JSON file. And both of the metadatas, they had the initial txt document from the datasets that they refer to, and then we can map with this txt document as a unique identifier to eventually find out which chunk corresponds to which ground truth object, right? So let's talk about results. Here we can see a lot of different graphs that I have, and the first ones will be from chunk size evaluation. Yeah, so you can see this is for arXiv domain, which is machine learning, and here is for PubMed for medical ones. Yeah, this is actually pretty interesting because in all of the cases the chunk size distribution was very high at the very beginning for all the medical domain chunking, and then it was already a little bit less here. Yeah, when in the machine learning field we have almost nothing here, and then it goes more kind of normalized. Yeah, we don't have a peak here and nothing here, but we have it all pretty well distributed, right? So let's see further. Here is for standard deviation method in machine learning. Here is standard deviation method in the medical domain. Here is for interquartile in machine learning. Here is for interquartile in medical domain. Here is for gradient method in machine learning, and here is for gradient method in medical domain. Again, as you see, all of the medical ones, they are pretty similar, yeah, and they're peaking at the very beginning, and then they have this very low kind of distribution of tokens here later on. When in the machine learning field, it's pretty much equal, yeah, all over the way, and it's good, right? So that's something important to notice. Now let's go more into the numbers. You can check them out on your own. I will not read out each number, but I definitely encourage you to go and see all the experiments here and verify the numbers. Maybe even run the experiment on your own because it's very easy to set up. So now let's talk about retrieval quality. Here are some of the results, but let's look at the graph, right? So here is for the medical domain. We have the precision, the recall, F1, and the NDCG and average precision. You can also check the graphics, you can verify the numbers. Again, it is all compared to ground truth, right? And now let's go into actual final scores. Yes, the most important one, why we're all here. As we can see for machine learning abstracts, we have standard deviation at the very top, then we go interquartile, gradient, and percentile methods with these scores. Yeah, so they are all pretty much equal to each other, but standard deviation is at the top, right? Then for PubMed, for COVID-19 introductions, we have standard deviation again at the very top, and then percentile, interquartile, and gradient. Gradient is actually very poor performance compared to the first place, right? So here the difference is just kind of 2, even less than 2 scores, and here the difference is almost 7 scores. Here it is also nicely represented in a graph way. So let's summarize it all into tier lists. As we can see, standard deviation chunker is at the very top for both domains. Then goes interquartile, but here it goes percentile, gradient chunker, interquartile chunker, and percentile and gradient, which is very surprising because both machine learning and medical domains are actually something that is highly correlated to each other. I mean, all the kind of words are highly correlated, as well as their specific domains, exactly as Langchain documentation says for gradient. Yeah, so it actually needs to be that gradient is the best method to use in such cases. But as we see from the evaluation, gradient is actually top 3 here, and here it's even top 4, the last place. Yeah, so very interesting. So let's have some discussion here, like what is the actual summary of what we did. Standard deviation chunker consistently achieved the highest score, which we saw, indicating its effectiveness, blah blah blah. In arXiv dataset, its higher mean chunk sizes and lower standard deviation suggest more uniform chunking, which may contribute to better retrieval performance. In the PubMed dataset, while the standard deviation chunker still ranked highest, the percentile chunker performed better than in the arXiv dataset, possibly due to difference in text structure and content between the domains. The gradient and interquartile chunkers showed competitive retrieval metrics, but varied in overall scores due to difference in chunk size distributions. These findings highlight that the effectiveness of chunking method can be domain dependent, as we saw. So what about math that is all behind it? We're using basic cosine similarity. So we are calculating angles between two vectors in a multidimensional space, providing a metric for orientation of the vectors. Here is the formula. You can also read about it more on your own. So precision, recall, and F1. Here is also all very basic, very simple. Precision is the ratio of relevant instances among the retrieved instances. Recall is the ratio of relevant instances that were retrieved over all relevant instances, and F1 is the harmonic mean of precision and recall. Here are all the formulas. Here is the average precision and also normalized discounted cumulative gain, and NDCG measures ranking quality, emphasizing the importance of the position of relevant documents. Here is the formula, where DCG is the discounted cumulative gain and IDCG is the ideal discounted cumulative gain. So what about conclusion? In conclusion, this benchmarking study provides a comparative analysis of Langchain semantic chunker, right? We have compared both medical and also machine learning domains. We identified the obvious winner, which is standard deviation, and we found out that a gradient method is not as good as Langchain talks about it. Something that might be interesting for you is to run the experiment on your own. The whole kind of benchmarking environment is very scalable. So if you want to include your own data sets or train it on more data than just 100 abstracts from each field, or include more different fields of studies, then it's all welcome. You just need to go and modify the data loader config JSON with, to include your data sets, then install dependencies from pyproject.toml. Configure your environment variables to include the OpenAI keys and also needed configuration to generate ground truths, and then go start main.py and see the results in the results directory. As I said, it's very scalable, so it acts kind of as a foundational analysis, and definitely further research is needed because I understand that 100 datasets from each field might not be enough to evaluate it properly, but due to time and financial constraints, I didn't proceed to run more experiments on it. I spent just 12 hours doing all of that, and I'm actually pretty happy with the results, so I leave it as it is to focus on more projects that I'm interested in. But if you have any questions or you would like to make any suggestions or work with me on that further, please let me know and write. Okay guys, so I hope you enjoyed this video. I hope you enjoyed the study and actually went through it and read it. I definitely encourage you to do so. If you like it, please star me on GitHub, start this project on GitHub. It will help me a lot. And also, if you have any questions or any suggestions, please write in the comments and we move on from there. I will go and work on the next ventures that I have in mind. Thank you very much for the watch, and see you in the next videos. Bye bye.